So what's the format of the questions?
It can be really anything. So if you want to be formal, we can do raising hands and then ask questions at the end. I mean, otherwise, usually I just prefer people to unmute themselves and then just ask and interrupt.
Okay. Yeah, that would be good. Because in this screen sharing setup, I'm not sure where I can see if there is questions or not.
Yeah, if people put questions in the chat, I'll probably just stop you.
Okay.
Yeah, and I think we can start. It's already 5 past the hour. Okay, so this week, well, this meeting, we're very happy to have Weiran Wang from Google. Um, Weiran, well, I think we the connection went all the way back to TTI. So he graduated from UC Merced, and then working in optimization and deep learning back then, and then he was a postdoc at Toyota Technological Institute at Chicago for 3 years, working with Karen Levescu and Nati Sribo. And then he went on to become a research scientist in Amazon and then Salesforce and now Google. And he sort of switched areas from pure machine learning now to speech processing. And he's going to talk about improving ASR with self-training and pre-training. All right, the floor is yours.
Okay. Thanks, Hao, for the introduction and the invitation. Today I'm going to be talking about some not too recent work. I think the two projects that I'm going to be talking about, they were roughly done in the summer and fall of 2019, and they were published in 2020. So some of the materials here might seem somewhat outdated, but it turns out these topics, they are currently very hot in the speech and the machine learning community. And I hope that some of the earlier intuitions are still helpful to discuss here. Okay, let's move on to the first part. So in the first part, I will be talking about semi-supervised ASR by end-to-end self-training. This was done with the intern Yang Chen, where I was at Amazon. And so the background of this work is that nowadays it's a common belief that with more data and a larger model, we can improve model accuracy with large-scale supervised training. However, collecting and transcribing huge data set is expensive and time-consuming. This is true even in industry when you have new applications, new application domains, or if you want to focus on the real world. The tail ASR. So the goal of semi-supervised ASR is to leverage large amount of unlabeled data to improve accuracy when smaller amount of supervised data is available. One of the oldest and the simplest method is self-training. That is, we use pseudo labels or decoding results of a current model on unsupervised data and treat them as ground truths to augment supervised training set. So currently, back then, end-to-end ASR greatly simplifies modeling pipelines and achieves superior performance if it is trained with sufficient supervised data. So a natural question to ask was, can we perform self-training with end-to-end systems? In this work, we propose a self-training method with an end-to-end system. The way that we do it is that we first train a CTC system carefully on supervised data. And then starting from that model, we iteratively perform two steps. We generate pseudo labels on a mini batch of unsupervised utterances, and then we use pseudo labels to augment supervised data for immediate model update. So the highlights are that we use token level pseudo label sequences, then per frame soft probabilities. And the pseudo labels are generated on the fly, then in one shot. And we perform data augmentation on also unsupervised data. With this technique, we were able to close a significant portion of the gap between a base system and Oracle system on a commonly used Wall Street Journal semi-supervised learning setup. So let's first review the supervised components we used to build the base system. The first component is CDC. So here is a short review. Given a input utterance X with T frames and a label, the corresponding label sequence of length L, CDC models the conditional probability of Y given X as the sum of probability of paths or alignments, which will reduce to the label sequence Y. Here, the reduction is done by removing the repetitions and then blanks. The probability of a path is simply the product of posterior of labels at each frame. After training, it is observed that the per frame posterior tend to be very picky. What it means is that blank is the dominant token at most of frames, indicating no emission, whereas in the non-blank frames, the probability is very close to 1. Since CDC does not explicitly model the label transitions, token level decoding is relatively easy. We can perform token level beam search to approximately find Y that maximize P of Y given X. In the case of beam size equal to 1, we have the greedy decoder, in which case we just pick the most probable token at each frame and then reduce the alignment to output label sequence. In case the token set correspond to characters or phonemes, but we want word level decoding, word level beam search can be done efficiently in the FST framework. In this work, we mostly use the greedy decoder for generating the pseudo labels because it's extremely efficient. The second component of our base system is data augmentation. It is a natural approach when you don't have any unsupervised data. And data augmentation was shown to improve ASR with different augmentation method. The specific data, the goal, the intuition here is that we want to use data augmentation to improve the base system so as to improve the pseudo label quality. The specific implementation we use is a spec augment. We perform speed perturbation with 2 additional factors and perform spectral masking of consecutive frequency channels and time frames. The perturbations are generated on the spectrogram on the fly. We are now ready to discuss the proposed method. The main intuition behind our method is to repeat pseudo label generation and augmented training so that the two can reinforce each other. This figure illustrates our approach. On the left part of the figure, we feed the inputs of label data X, and we perturb it to get the noisy version tilde X, and use the corresponding ground truth label Y to compute the supervised CDC loss. On the right part of the figure, we feed the clean inputs of unlabeled data X. We use the current acoustic model to predict its label sequence Y star by beam search. And then we use the noisy version tilde X and the Y star to compute the CDC loss on the unsupervised data. So our method can be seen as optimizing the following objective function, which has 2 terms. The first term is the average CDC loss over NL labeled utterances. And the second term is average the CDC loss over the NU unlabeled utterances. The 2 terms are combined linearly with a trade-off parameter gamma. We perform alternating optimization of the objective over the 2 set of variables. Right? The first set is the acoustic model weights, which is denoted as theta, and the second set of parameters we're optimizing over is the label for the unlabeled, is the hidden label for the unsupervised data. In particular, the optimization over the discrete label sequence of the unsupervised data was done by beam search. This is approximate. and we optimize over the custom model weights, which appears in both terms with gradient descent. Our work was initially motivated by the work of unsupervised data augmentation, or UDA. The authors proposed to use a consistency loss on unsupervised data. Although they didn't work on sequence data, their consistency loss was more or less translates into the equation here, which measures the per frame k-out divergence between the posterior of the clean data from an older model, which is denoted as theta old, and the posterior of the noisy model from the model to be updated, which is theta. Note that if there is no data augmentation, so in other words, tilde x is equal to x, then the loss will be 0 if you set theta to theta old. In this case, there will not be training signal from this loss term. Our method differs from UDA in that it works even if there is no data augmentation. The intuition from us is that we think the well-trained base system, it generates a discrete level sequence which can provide stronger training signal than the soft targets. In terms of related work, self-training was well studied with traditional ASR systems. A lot of prior works found that the quality of the pseudo-label plays a crucial role in self-training, and much of the research in this area was dedicated to measure the confidence and perform data selection. I think our method is elegant because of the spiky behavior of CDC posterior, meaning that the pseudo-labels are high confidence predictions from the model. And in recent years, there are other ways to do semi-supervised learning with end-to-end systems, including cycle consistency loss, which combines ASR systems and TTS systems. So the intuition is that ASR output on unsupervised data should be able to reconstruct the audio by TTS, whereas TTS output should be recognized by ASR. Another approach to encourage is to encourage decoding results on unsupervised data to look like natural utterances as judged by a criticizing language model. I want to mention that I think that the recent work by Facebook, which trains on unpaired audio and text, they used a similar idea to criticizing language model. When you don't have paired, when you don't have the paired ground truth for the audio, then this is something that one can do. I think our approach is simpler than this work in the sense that we do not have complicated text-based neural networks. We don't have TTS, we don't have extra language model. And rather, our beam search results from the custom model are immediately fed back to the custom model for self-training. When we did this work in the summer of 2019, there was one concurrent work from Facebook. The authors used attention-based 6-to-6 system to perform self-training. Different from us, their work did not use data augmentation, and they used the word-level language model and ensemble models for generating pseudo labels, but in one shot. More recent work, as our paper was published, more recent work has started using the similar intuitions of data augmentation and data augmentation on unsupervised data, and also iterative pseudo label generation. In experiments, we work on a standard Wall Street Journal semi-supervised setup where we use 15 hours of supervised data and 81 hours of unsupervised data. Our acoustic model has bi-directional LSTM architecture, and it was trained with phone-based CTC loss. On this slide, the table shows phone arrays of base CTC system trained on 15 hours. We observed that SpecAug clearly improves the performance reducing the depth phone error rates from 18.5 to 16.8. Based on this observation, we will always be using data augmentation on supervised data. We then continue with self-training from the base system for another 30 epochs. We use W to denote the beam width for pseudo-label generation. We see that even with greedy decoding for pseudo-label generation, we can significantly improve the base system, reducing the phone error rates from 16.8 to 11.5 on the depth set. And to demonstrate the effect of data augmentation on unsupervised data, in the last row of this table, we turn off the spec-aug on unsupervised data, and the depth phone error rates degrades from 11.5 to 12.8 or so. So this means that data augmentation on unsupervised data is useful, similarly to the case of supervised data, even if there is some label noise from the pseudo labels. Now this slide shows the curves, the learning curves of the depth phone error rates for different values of the trade-off parameter gamma. We observe that the performance is stable for a wide range of gamma values, regardless of whether we augment the unsupervised data or not. Also, the best gamma is around 1.0, so the weight on the two terms are more or less balanced. The weight on the loss on the supervised data and the loss on unsupervised data are more or less balanced. This indicates that the label noise on the pseudo labels was mild. We also varied the beam size W, and we found that larger W would significantly improve self-training performance from 11.5 to 11.3, slightly improvement. If we use W equal to 15, this is achieved at the cost of a drastic increase in terms of decoding time for pseudo-label generation. And to show that discrete labels provide stronger training signals for self-training, we implemented a sequence version of UDA, which uses per frame posterior divergence for consistency loss. The method achieves depth phone error rates of 14.3, which is clearly worse than our method. And finally, we compare with one-shot pseudo-label generation. We use the base system to generate pseudo-labels for all unsupervised data at once with a larger beam size W equal to 20. These pseudo-labels are then fixed during self-training. This approach obtains a depth phone error rates of 13.7. This shows that as the Kuss model is being improved, the fresh labels, they have higher quality than those from older system. And on this slide, we show the learning curves of different methods on the depth set. All semi-supervised method continues from the base system at epoch 35. Observe that our method, which corresponds to the red curves, outperforms the others by a large margin. Note that our curves keeps going down continuously, demonstrating that the two alternating steps reinforce each other. Finally, we perform FSD-based decoding with a trigram LM to obtain word error rates. The base system trained on 15 hours of supervised data achieves 11.4% test word error rates. On the other hand, the Oracle system that uses the ground truth labels for all 81 hours achieves 7.8 or so test word error rates. Our self-training method achieves 9.8, which closes almost half of the gap between the base and the Oracle system. As for future directions, we could be using word-level decodings to further improve the pseudo-label quality, and RNT is another promising model to improve token-level decoding. I think this is largely being done. We could also use multiple top hypotheses simultaneously for unsupervised data in self-training, also considering the confidence of each hypothesis. And I think this is also done to a large extent. In the end, for this part, I want to mention a use case for this method, which is federated learning. So in this case scenario, all the devices can start from a global model, and then each of them perform self-training locally in the background using the customer data. And then these models can communicate their updates sporadically. In this scenario, since the decoding time is less of a concern, we can use the most accurate method for pseudo-label generation. And because we don't update the global models very often, latency probably can be tolerated. That will conclude this first part. So we can have, if there is any questions, I can answer now for this part.
Hi, Weiran. I have a couple of very quick questions. So one of them was about the balance between the supervised and unsupervised data. And the second one was, you seem to be quite pessimistic about using soft labels. Do you have any suggestions where they might be better than the hard labels that you are using? Thanks.
Yes. So for the first question, sorry, I forgot the first question.
So the first question was about the balance between the supervised and unsupervised data within one mini batch. I imagine you have both supervised and unsupervised within one mini batch. So you have two NL and NU. So what was the balance between them?
Right. Okay. So for this work, I used a pretty simple way to balance. So so I think that for the worst regional setup, the amount of unsupervised data versus the amount of supervised data was like 4:1 or 5:1. I think I had because they are not too different. So I think I used the same in the mini batch. I used the same amount of. I mean, actually, I have two mini batches. So one mini batch is for the supervised data, and then the other mini batch is for the unsupervised data. I think, if I remember correctly, I used this. The mini batch size for the two are the same. It could be. I'm not sure. I might have also used slightly more utterances in the unsupervised mini batch, but in any case, the loss is going to be the average for each of the mini batch, right? So we have a mini batch for the unsupervised data. We compute average loss per utterance, and then for the unsupervised mini batch, we do the same. And I feel like for this particular data set, the amount of noise in the pseudo labels was really mild. So I would assume that, and you also see that the gamma doesn't really matter that much. I would say that if you vary the amount of unsupervised utterances in the mini batch by a few times, it wouldn't matter too much. I haven't. And for your second question, you're asking when do you think soft labels might be better? I haven't done very extensive study for this method on other domains. I feel like maybe for the perhaps for the classical system where we don't have where the posteriors are all more meaningful, maybe in that case, the soft labels would be better, and also depending on the quality of the base system. If the base system, the quality is not so great, I would imagine that maybe soft labels would have more like dark knowledge there. But I feel like for reasonably well-trained base system, I still feel like based on my study that the discrete labels have stronger signals. But I have to justify that, I have to do more experiments on more challenging domains.
Perfect, thanks.
Thank you. Okay, if there is no other questions, shall we move to the second part? Okay. So for the second part, I'll talk about unsupervised pre-training of bidirectional speech encoders via mask reconstruction. This is joint work with Qiming Tang and Karen Levascu. Let me first introduce the background of this work. So unsupervised pre-training has a long history in speech recognition. For speech recognition in particular, we used to do pre-training of the feed-forward networks for acoustic modeling in a layer-by-layer fashion with unsupervised learning objectives such as restrictive Boltzmann machines or denoising autoencoders. And this was often done on the same supervised training set as used for acoustic modeling. However, pre-training has become less popular due to the development of better initialization, non-saturating units, better architectures, and methods for controlling generalization, etc. So at the time, recent work has begun to reconsider the value of unsupervised representation learning, where people trained representations on large amount of unlabeled data and for use in supervised training on small label data set. This is to some extent inspired by the success of unsupervised pre-training from the NLP community, where representations of words or subwords trained on a large amount of text data have been shown to be more or less universally useful in various downstream tasks. Because both text and audio data have a temporal structure, we hope that pre-training for speech will also have similar success. This is a summary of our work. We developed a pre-training method for bidirectional speech encoders and specifically LSTMs. We're inspired by bird-style pre-training and in particular the use of masked reconstruction loss, and we adapted the idea for speech recognition for speech processing since we have continuous inputs rather than discrete tokens. We are also inspired by spec augment and apply masks on both the time and frequency domains. Our contributions are the following. We improved performance for both character-based and phone-based ASR, and we propose to use domain adaptation techniques for pre-training with data from different domains. The bidirectional LSTM encoder can be dropped directly into many offline ASR use cases. And there are several lines of related work. There have been a lot of work from the machine learning and the vision community, which share the common motivation of maximizing the mutual information between features and inputs. One popular technique for maximizing mutual information for sequence data is to learn a current time step representation that is predictive of future time step input. We note that such techniques rely on the notion of future, which often constrain the encoder architecture to be unidirectional. I want to mention here that I think for Wave to Vec 2.0, the features are almost full. I think it's full context. So CTC still works in the full context scenario. And one line of work is the zero speech setting, where we want to learn discrete phonetic or word-like units or representations that can distinguish among such units. And this can potentially be done with multi-domain, multi-model data. I would like to discuss in more detail concurrent work, which also uses ideas from BERT. The recent work back then from Facebook was performing pre-training in 2 stages, where the authors first extract discrete representations of speech frames with a mutual information-based objective. And once they have the discrete representations, just as in the NLP setup, they apply BERT learning to extract continuous features. Finally, they use BERT features as input to train ASR systems. The authors performed pre-training on LibreSpeech and obtained state-of-the-art results on Timid and Wall Street Journal. We note that the discrete token set was quite large, containing tens of thousands to millions of tokens. So the computational cost of this approach is very high. We also note that without BERT, actually, the discrete representations themselves do not outperform the baseline features. And we can now describe our method illustrated by the figure on the left. We apply a certain number of masks in the frequency axis with random width up to 8 at a time, where the input feature dimension was 40. And we apply a certain amount of number of masks in the time axis with random width up to 16. For the mask pixels, we set the value to 0. And we then use a bidirectional LSTM to map the inputs to extract high-level features, per frame features, which is 128 dimensions. And we use a feed-forward network G with 2 value layers to reconstruct the input features independently for each frame. And in terms of the loss, we measure the reconstruction loss only at the masked positions, which is the loss for joint training F and G. We retain the LSTM layer of the F mapping, and we use it to initialize the downstream ASR model training. In this work, we have applied also speed perturbations to augment the unsupervised data. And the speed factors are 0.9, 1.0, and 1.1. So it was pretty standard speed perturbation. And we now demonstrate the effectiveness of the pre-training representations for ASR. The ASR system we use is CDC, one of the simplest end-to-end systems. It maximizes the conditional probability of label sequence given the input acoustic features, marginalizing all possible alignments. We use the FSD-based approach for word-level decoding, following ESON. We experiment with both phone and character as modeling units for CTC. In this work, the ASR training and evaluation are always done on the Wall Street Journal dataset. And we have 2 versions of the training set. The SI84 partition has 15 hours of speech, and the SI284 portion has 81 hours of speech. Pre-training is performed either on Wall Street Journal SI284 or LibreSpeech, which contains 960 hours of speech. This table shows the depth set phone error rates for phone-based CTC systems with different number of frequency and time masks for pre-training. Here, pre-training is done on 81 hours and fine-tuning is done on 15 hours. The baseline without pre-training gives 18.5% phone error rates. And we see that most masking parameters lead to improvement over the baseline. The special case of no masking or MF equal to MT equal to 0 correspond to actually a normal autoencoder training, which does not provide improvement, probably because reconstructing clean inputs is quite easy when we're conditioned on the full context. From this table, we set MF equal to 1 and MT equal to 2, which are the number of masks we're going to be using for pre-training all phone-based systems. On this slide, we fix the pre-training data set to SI284, 81 hours, and vary the amount of supervised training data to be either 15 hours or 81 hours in combination with data augmentation using spec augment. Comparing the second and the third column, we observed large improvement from pre-training, particularly when the amount of supervised data is small, which is the SI84 case. But there is not improvement when we increase the supervised data to 81 hours. This motivates us to use further increase the amount of pre-training data. We now use the LibreSpeech corpus for pre-training, which contains 960 hours. The challenge is that now there exists a domain difference between pre-training and fine-tuning. Let us compare the fourth column and then with the third column. So we observe that if we directly use LibreSpeech pre-trained networks for fine-tuning, there is still no improvement for fine-tuning on 80 hours. There was improvement in the case of fine-tuning with 15 hours. And to solve the domain issue, we use a classical adaptation method called linear input networks, which inserts a linear layer between the input and pre-trained networks. And in the first few epochs, we only train the linear input networks, and afterwards we fine-tune everything together. This yields the results in the last or the fifth column, and we now observe improvements for fine-tuning on 81 hours. We now switch to the character-based systems. The masking parameters are tuned again in the same setup as the phone CDC, and we use more masks in the frequency domain. For the results table, we perform pre-training on LibreSpeech and fine-tuning on Wall Street Journal. Again, we observe the importance of domain adaptation with linear input networks. Moreover, there are consistent gains across different fine-tuning setups, and the gains from the pre-training and supervised data augmentation are additive. So even if there is spec aug on the supervised data, we could achieve improvement by pre-training first. And in this slide, we show the learning curves on the depth set in terms of both the character error rate on the left and the CDC loss on the right, with and without pre-training on LibreSpeech. We observed that the red and the purple curves, which use the pre-training and adaptation, show less overfitting and converge to lower error. So this means that the pre-training helps generalization. This result table shows the word arrays of baseline and pre-trained character systems when we pre-train on LibreSpeech and fine-tune on SI284. Our baseline has similar word arrays to the one reported by Ethan. And the best performance is achieved by pre-training combined with data augmentation. This table shows that more accurate pre-trained acoustic models, even if it's a token level acoustic model, it also leads to improvement when we decode with the language model. And the improvement here is like a bit over 10% relative. Okay, so the conclusion for this part is that we have proposed a new method for pre-training bi-directional speech encoders by mask reconstruction, which leads to consistent improvement for CDC-based ASR with ASTM-based architectures. I'll list a few future direction here. But some of them are already done. So we could try different architectures including transformers and ASR system, including attention or RNT, etc. I believe these are being done. These have been done, and different ways of resolving domain difference. I want to mention that last year, when I switched to using transformers, the linear input networks doesn't really help anymore. So maybe the domain difference was it was particularly useful for LSTM-based models, which are harder to optimize, perhaps. And finally, we need better understanding of the features to understand what they really learn. I think there is some relevant work in this direction as well, which are already being done. And before I finish, I want to mention some more recent work. So I think at this point, one of the most prominent approach is wave-to-vec, and in particular wave-to-vec 2.0, which actually combines the idea of augmentation at a higher level features and contrastive loss. They optimize the two jointly. So this loss looks like the following. We use a high-level feature at time t as a classifier to distinguish positive samples. I mean, by samples, I mean input frames of near future. We want to distinguish them from negative samples, which are far away frames or frames of sequences in the mini batch, of other sequences in the mini batch. One way to interpret the CPC kind of loss is that it maximizes the lower bound of the mutual information between high-level features and inputs. So here the key is that the mutual information is between features and inputs. I had some more recent work published in iClear this year, was that we investigate a different kind of mutual information. It's the mutual information between high-level features and high-level features that are some time steps away. And the idea is that we want the features in the latent space to be predictive of future. Now, the mutual information usually is hard to estimate, but based on joint Gaussian assumption, there is a closed form estimate of the predicted information. And we use this loss to regularize masked reconstruction. So masked reconstruction is in some sense, if you interpret it as an autoencoder, it's trying to maximize the mutual information between the features and input. Now, this additional predictive information is trying to maximize mutual information in the latent time steps, latent space over time. So the figure at the bottom is a synthetic example, and which I think can best demonstrate the intuitions. So the data was really a 3D Lorentz attractor. It's a physical system you can generate with differential equations. We lifted this system from 3D to 30D and added heavy noise. And the goal was to recover the latent 3D trajectory. We compared a bunch of methods. So DCA was was trying to maximize the predictive information, but using only a linear mappings. So this was clearly not sufficient. And our deep predictive information was actually extending this approach to using nonlinear neural architecture. The CPC was working reasonably well, and if we only use predictive information, we get the PI only column was for only maximizing mutual information, predictive information. This tends to have some degeneracy, and masked reconstruction works relatively well for low noise setup, and with the highest with the lowest S signal to noise ratio, we need to combine the two, which would generate the trajectory as shown in the last column. So I think that the two kinds of mutual information are probably complementary, and it's it's a reasonable idea to combine them. Based on the more recent literature, it looks like the research of pre-training is moving in the following directions. So the first one is to scale up to large architectures, which tend to be more data efficient. So Google has done a lot of work in this direction. What they found is that if you there is more gain actually from pre-training if you use large architecture. And once you pre-train the model, you can converge faster by using less fine-tuning steps. You can converge to a as good or even better position than if you started with a small architecture. And people have already shown that it's a good idea to combine both pre-training and self-training. Their gains are additive. Recently, there was more work in pre-training with unpaired speech and text data, these proposes challenge to develop new methods and architectures to leverage them. And personally, I was interested in other learning objectives. It looks like CBC works well, but is it the best? We don't know. I think it's possible to have additional gain from using maybe probabilistic and variational sequence models. And with that, I will conclude my talk. Thank you.
All right. Thanks for the great talk. Yeah, so if any of you have questions, feel free to unmute yourself. I have a ton, but I'll let you guys go. Maybe just to kick off the Q&A. So there is one from Rohan in the chat, and I think it's about the first part. So he asked how much data augmentation is required for good performance. I mean, if training data is of 15 hours, then how many hours of data augmentation is better? I suppose you're doing on-the-fly data augmentation, is that right?
Yes, so we are using spec augment. So spec augment will randomly use some masks. So even if it's the same acoustic data, when it's appearing in the training at different times, a spec aug would use a different mask on it. So in a sense, it's also using 15 hours of speech for data augmentation, but there is a lot of variations of the 15 hours. Does that address the question? Yeah, I feel like spec augment or this kind of on-the-fly augmentation was really convenient, and they are very useful in terms of improving the performance. But you could also do augmentation at the signal level, adding background noise. I think that's something that spec augment probably cannot do if you want to be robust to that kind of noise. So I would imagine that based on the application, you could have additional gain by first perturbing the audio with some multiplier, and then add them into and use both the clean version and the noisy version with background maybe, and then use the joint data set, and then still at training perform augmentation on the fly. I think that probably would give the largest gain. We didn't do augmentation at the audio level for Wall Street Journal because it's already pretty clean. And we want to test in a clean scenario. That's why. Yeah.
Mm-hmm. There is another question in the chat. Would you say that masking the input and reconstructing the masked part leads to more informative features than a regular autoencoder, where you
yeah, I think that's true from the observation. So I showed a few a few slides earlier that we did try. We did try the normal autoencoder. Yeah, so here. So the MT equal to MF equal to 0 case was actually was a special case. In this case, we didn't do any masking, but we're trying to do LSTM feature extraction and then normal and then reconstructing the entire input, not just because there was no mask, so we reconstruct everything. And this was not helping at all because condition on the LSTM features, the LSTM already sees the full context, so reconstructing is quite easy. But that would probably, because it's too easy, that probably discourage you from learning more context information. Whereas if you mask some portion of the inputs and you're forced to reconstruct, you have to learn the structure of the input, right? The time structure, and then in our case also the frequency, the structure in the frequency. So in this case, I would say that the features are more has more context, which probably is helpful for ASR. But in the end, the two losses are mask reconstruction is a proxy for learning good features, but in the end, the goal of the two losses will diverge. So I should say that it's probably a good idea to do more careful model selection. For example, if you do pre-training, you don't want to converge to the best reconstruction error, but maybe pick checkpoints along the way and see at which point you get the best performance. This is something we didn't do in the paper, but I feel like this is probably going to help.
On a similar note, you can also so if I understand this correctly, you are reconstructing only the bands that you masked, right? So in principle, you can reconstruct the entire thing, but with the masked input. Am I correct?
Yes. Yes, but again, I feel like the part that you already see in the inputs, reconstructing them is easy. I think Karen's group conducted some study in this direction. So what her group found was that you could make the task even harder to not reconstruct the entire mask portion, but only the middle part, the middle slice of the masks. That seems to give even better performance because along the edge of the masks, you probably can still infer the inputs by looking at certain smoothness structure, but the middle part of the mask is even harder. It really forces you to learn context features. Mm-hmm. Yeah. So in this case, in this paper we did not reconstruct the seen part, the part that's already seen in the inputs.
Yeah, I just feel like if you reconstruct everything, then the framework is more like the old school denoising autoencoder, and then you have all the nice probabilistic interpretation associated with it, and so that comes back to your future work slide and also wave to vec 2.0. So if my understanding is correct, wave to vec 2.0 is trying to do contrastive loss, but the target is the quantized ones. And then really there is no, and that they're just doing masking and trying to do contrast on everything. So it's really just like an autoencoder in some sense. I wonder if you have any comments on that. Yeah.
I didn't play around with wave to vec 2.0 myself. So one thing that was the one thing that seems to work very well for them was the discretization. I don't know how much gain that was giving. Maybe it was already shown in the paper. But I don't know, from theoretical, I mean, more like at the more fundamental level, I don't see like what's the clear advantage of using discrete representations versus continuous. Maybe there is some like control of the information bottleneck in some sense. But other than that, it's pretty much a deterministic model. My intuition of looking into variational model was that if you look at autoencoders and variational autoencoders, it looks like variational autoencoders really was learning something different from deterministic autoencoders. So the common intuition is that you're modeling the uncertainty of the data. I feel like that's something not sufficiently looked into in the current pre-training. And the variational models give us some probabilistic interpretation of the generation process. I feel that could be a potentially useful thing to look at. But it looks like Wave2Vec 2.0 was really working well. Different groups can replicate, and the more data, the better. The larger model, the better. So there is a lot of challenging scaling up. But I feel like there is probably also more things to look at from a machine learning perspective. I don't know, maybe if once we switch to, if we use probabilistic models, the training would probably be slower, but maybe there is additional performance gain. I'm not sure.
Oh, there is a hand up. Peter, do you want to just speak?
I have another question. So thanks for your talk. The question is a follow-up basically to a previous answer that you gave, where you explained that having features which better take the context into consideration are helpful. And my question is, do you think there's a limit to that? So, I mean, ASR is a monotonic problem, and typically we would think that features somehow should also contain mainly local context. So do you think there's a limit to how much of the sequence should be considered for creating one representation?
Yeah, so that's a good point. And I think one way, like one experimental approach is to vary the amount of masks, especially in the time domain, because we know that the longer the masks, the less data you are seeing in input, and you want to reconstruct them is a harder problem that requires more context. And I feel like it's not the case that always the larger the mask, the better. There is a limit to that. But the other thing is that I'm not sure whether the limit is also kind of conditioned on the amount of data we have. So I think that perhaps and also for maybe for each data set, depending on how long the utterances are, the kind of the context is also different, right? So I feel like there is a limit, but the easiest way is probably to do it to verify it experimentally. I don't know. For acoustic modeling, probably it's the case that for acoustic modeling, it's probably the case that you don't want very long context. On the other hand, for language modeling, it's probably the longer context, the better. If people, I think there is this viewpoint that pre-training is actually also learning a language model structure from the data, then in that case, maybe it's better to have a longer context. But I agree with you that if you want to do classification of the tokens, shorter, a reasonably long context is probably enough. I don't know the answer to that question. And in terms of performance, probably a good idea to vary the amount of masking for each data set. But I don't know, like theoretically, whether it's the longer the better.
Okay.
Hard to say. Yeah.
Thank you.
Yeah.
Any more questions? All right, if not, and I think we can wrap up. So thank you so much, Weiran, for the great talk. And
No problem.
Thank you all for coming. And so 2 weeks from now, we will have another a talk on phonetic segmentation, which is also a completely different and interesting topic. So stay tuned. I'll see you guys 2 weeks from now.